Um,
Now we are live.
Broadcast. We are live. And
I'm seeing click add videos to playlist to search videos to share. Okay. I have no idea why I'm seeing that right now. Okay, back to you.
all right. Good morning, Michael. And today is the May 6th, and we will be soon starting our weekly hangout. And how are you today?
I'm doing very well. I'm enjoying the warm weather and pleasant air outside.
All right. And the topic for today, if you're ready and when you're ready, we can get going with that.
Okay. The topic for today is to go over a little bit more about the lunar networking, information systems, especially the space segment. I did a little bit of reading and put together a few notes on that. Are you able to see my display?
Yes. Deep Space Information System for LunarCubes space segment.
Okay. Let's see if I can change the view here. I wonder how I get rid of this display over here. I press slide only and it's not all.
This is Keynote?
Yeah, this is Keynote. I'm trying to find a way to close the slide Outlook side over here. Oh, wait a second. There. Okay.
Yeah. Excellent.
There's those icons also double as toggle switches. Okay. So just spend a few moments going over the space segment, and I'm going to take a little bit more of a systems viewpoint of the space segment this time, because we've talked about, in previous discussions, we've talked about some of the vision. And Abraham, feel free to interject and talk about the vision and how that fits in with our plans. Okay, so that's interesting. How do I go to the next slide now? I'm pressing, no, not that one. All right, now you're looking at my face, right? Are you still there, Abraham?
Yes, I'm there. I'm muted for better audio.
Okay, now what are you looking at now?
Your face.
Okay. So now I'm trying to move from one slide to another slide. Start the screen share. I'm back on the display. And it seems that no matter what... Okay, we'll try it like this. All right, so how do I advance the slide? I just suppose I have to click on it. Very well. Okay, so let's take a look at the space segment for information systems. If you take a look at a systems level decomposition, you take a look at the space segment. That's the deployed part or the remote part. Take a look. Another way to factor it is to look at the ground segment of the system. That's the control and operations center. It can also be the ground infrastructure associated with your telecommunications. So, for example, on the Earth, that would be the deep space network. If you're talking about an interplanetary system, and finally, the third aspect is to get the connection between those two segments, the communications between, say, the space segment and the ground segment. So today we're mostly going to focus on the space segment of that trilogy. Now, the motivation for most space missions is to put a sensor or some other data producing element out in a place where it can actually do its work. For example, if you're talking about planetary science, you're going to put a rover or a remote sensor in the vicinity of that target, and it will generate data. And the goal is to get that data back so that people can look at it. So generally, information is the primary reason we deploy those space systems. When you're taking a systems level approach, there's generally three key or critical resources that go into the definition and design of that system. And those three elements are information, energy, and mass. So those are the main three dimensions of a system that you're looking at when you're putting together those systems. And those are the things those are properties of those assets that you're sending out there to produce value for you. So today we're focusing mostly on information. This is the information systems special interest group for Deep Space Cubes. And there are other thrusts of our effort that Russell, Cox, and Fletcher Engineering and Abraham are looking at, which focus more on the mass and the energy. Although to make a complete solution, you need to tie all of those together. So information is the prime reason, our main motivation for deploying space systems. These can be for a number of different reasons: science, intelligence, communications, coming up with operational data, and also technology development too. Information flow is critical for the decision-making and spacecraft operations. If you think about spacecraft health and safety, it's not just science and payload data that's coming back that's important. It's also the data that's being generated by the subsystems themselves that tell you how the spacecraft is operating, and it's important to monitor those so that you know how the spacecraft is going to operate over time. There's generally a trade-off between using the spacecraft as a resource and the value of the data that, or whatever the value is, and generally it's going to be data, the value that's going to be produced by that asset over time. So that's making a decision about whether to continue the mission, whether to expend resources, or even expend the spacecraft. You have to balance that against how long you think the spacecraft is going to live, and also against how much information you're going to get from any particular action. So this data, things that you're going to use the data for, commanding the spacecraft, the data or capacity for it to increase or generate the data that is the reason why you're sending the spacecraft there to begin with. Then there are also various kinds of automation and autonomy in running the spacecraft. Those are all part of the information flow. So those are two primary reasons. Those are two main reasons why you're looking at the space segment, the information flows in the spacecraft. It's a very important thing for actually designing your system. Now, when you're talking about the space segment, if you're taking a mission viewpoint, which is, okay, we have a particular science or other mission, and we need to put our instrument or spacecraft somewhere so it can produce value for us, you're mission focused. You have the goal of the mission, and the space segment of that, the deployable part of it, is a means to an end. It is a solution to that particular problem. The components of that solution, covering for mission viewpoint, you have the communications, which is bringing that value back to you, or putting it where it's supposed to be. Command and data handling, that's where you're controlling the spacecraft, keeping track of spacecraft health and safety, and also taking the mission critical information, its reason to exist, taking care of that. So that's the command and data handling part of the spacecraft as well. Now, because in general you're not in complete 100% uninterrupted contact with your remote asset, you need to have data storage. So generally, with the advances in sensor productivity and sensor quality over the years, you can put together a sensor package that will generate more data than you can send back, no matter what sort of telecommunications technology you're using, even if you're talking about optical. So you can generate a huge amount of data. You have to balance that data generation capability with the ability that you have to send data back. So some properties of the telecommunications part is when is communications available and what is the bandwidth. And also there's a latency issue as well, depending upon how far away the spacecraft is, and precisely what are the links in the communications chain, and going from your remote asset back to the entity that is going to use that data. Embedded processing is an important component of all of this. And again, you have those two factors: the engineering, the health and safety, and the command and control, which is actually working the spacecraft, executing the spacecraft behaviors. And then you have the payload subsystems, which are going to provide you the value for your particular mission. Now, there's a different kind of mindset you have to take when you move away from a mission-centric viewpoint to something where you're supporting a mission. And my point there is when you go to infrastructure. You can say that an infrastructure is a different kind of a mission, or it's a multiple mission, or support segment for the spacecraft. But really what's happening with the Cube spacecraft and all of the spacecraft which are going to the moon, you have the potential for having a lot of deployed assets in cislunar space. So you'll have a number of spacecraft, you'll have a number of conventional spacecraft being sent to the moon, which when they complete their mission, they're still going to have some excess capacity available, capabilities that will still be potentially useful in cislunar space. So you're going to have these assets just essentially sitting there. And one of the things that Flexure Engineering is looking at is how you can tie those together to actually provide infrastructure, so that part of a particular solution, a specific solution for a mission goal, you can plug in to an infrastructure that already exists. And there are plenty of examples for this, and just some space-oriented examples, particularly dealing with information systems. You have the tracking and data relay satellite system, the TDRS, which really provided a revolution in spacecraft communications in Earth orbit. For example, the TDRS system plays an important role in maintaining communications for the human spaceflight program. For example, providing high quality coverage for, say, the space shuttle and also the International Space Station. The TDRS system, there are multiple spacecraft in the TDRS system, allowing these different assets to be able to communicate with the Earth, with the users of the space station, the space shuttle, and subsystems thereon. The TDRS provides much better coverage in time and bandwidth than you'd get if you only had, say, ground stations to work with. So in fact, when people are putting together mission plans, they rely on the infrastructure of TDRS as part of their mission architecture. Another system, and by the way, the TDRS system was designed with that in mind. Now, an ad hoc capability that has been put together around Mars. So Mars has its own communication systems now, where you have a network of assets out there, and people are using, for example, the Mars Reconnaissance Orbiter as a telecommunications transfer point, and they're starting to use the major telecommunications assets on different Mars spacecraft to essentially trade communications from one asset to another. So this is something that we're looking at. Well, you can do this around the moon as well. So going into the moon, going into the lunar situation, and Russell has some very nice slides and lists. You're going to have a lot of assets going up. They're going to be around the moon and what we can do is that we can tie these together into a network, and hopefully with a little bit of foresight, we can make it easier to put these together into an ad hoc infrastructure that we can then take advantage of for cube-enabled missions. Some of the things that you're going to be working for is what sort of software elements you need to enable that sort of system. So there's going to be software protocols, communications protocols, and having the different systems talk to each other. And so part of our own special interest groups interest is going to be the software stacks and the different capabilities that people are putting together. We're not focusing. We do have an interest in the hardware aspect of this, but for our own information systems segment, we do tend to focus on the software and the protocols and enabling, coming up with enablers for the communications and processing. So in summary, just mainly want to point out that mission and infrastructure are different aspects of the problem. Most of aerospace practice has been focused around mission-oriented goals, mission-oriented architectures. And what we're proposing here is somewhat different, where we're saying, okay, once you have these missions in place, let's put them together into an infrastructure as well. And you can put together an infrastructure, but we're trying to make that real so that you can have an infrastructure in place to enable a much broader range of missions. We're going to have multiple missions to the moon, and what you might say are over-engineered in order to get reliability. You're going to have extra assets and capability, extra capacity in space, and we want to be able to use those. Those can be the building blocks for your network infrastructure. Hundreds of cube efforts are in process right now. It's a very dynamic situation that we have. So how do we stitch those together? How do we synthesize services into new capabilities so that we can actually synthesize those new capabilities into mission capabilities and really democratize access to space? So that in a nutshell is a starting point for a discussion into the space segment, issues of concern, and the next steps from here would be to get into some of the details of upcoming efforts and the what you might say are the tall poles in the tent that are going to keep you away from realizing a vision of hundreds or thousands of communications or sensor nodes in cislunar space. How do you take all the assets and capabilities that are going to be put in there and provide essentially a backplane in cislunar space that you can plug your own specialized mission into? Yeah. So that's the presentation for today on the space segment.
Excellent. That was quite informative and very interesting. Help me go back a couple of slides, like the ones we had the TDRIS. Yes, the space segment here.
Yes.
Here, the Mars constellation, if it exists, they're also part of the TDRIS, which is around the Earth. Can you kind of elaborate? It's treated like a subnet type of topology, or they're all homogeneous flat architecture? When we attempt these in Moon, where would these fit? Any thoughts?
your question is how you say subnet architecture. What?
Like in terms of hierarchy, if you try to arrange that in hierarchy,
Right.
I'm assuming the orbital assets around the Earth connected to the ground station is probably the one on the top, and the one in the Mars is a branch out of that as a another subnet, because we have in Mars about 3 or 4. So I'm assuming there's only one arm reaching out to the Mars, or if there are 4 assets there, are they able to individually and simultaneously talk to the TDRS assets around Earth orbit?
Yes, I have not looked into the details for the subnetworking or networking arrangements that are currently possible with those sorts of assets. It is my understanding that there's a lot of manual coordination in setting up the communications, particularly for interplanetary work. So for example, you have teams of people who are coming up with mission plans and command sequences for controlling the different components of something like TDRS. It's not really a fire and forget sort of system. You're going to be very you're going to very carefully come up with the particular plan for how you're going to set up a particular communication between a couple of different assets. And then you're going to very carefully construct the command sequences to those remote segments so that they are in the correct configuration, the right attitude, the right power configuration, the right equipment configuration, so that you can actually have those multiple assets communicate to each other. It's a rather large. It's a very intricate dance that you have going on when you have 2 of these space assets talking to each other, because you are doing things at, you can say arm's length, but it's much more than an arm's length. You're being very careful about how you're going to set up the state of each of those assets so that when you execute, they put together the coordinated activity that you're trying to achieve. For example, if you have 2 communications spacecraft talking to each other, particularly if they have very different mission profiles. For example, something going around Mars and something going around the Earth. So it's something that's you can. I don't know. I could not tell you right now how automated that is, or how autonomous those sorts of things are, because I'm just not. I'm just not in the operations room putting together those mission plans.
Okay, I got a picture of that. And you know, these TDRS assets in the Earth orbit, I assume it includes ISS as an asset too?
Sorry, please repeat your question.
The question is, like, ISS is also orbiting around the Earth.
Right.
And is it treated as one of the assets, or it is treated as a client, which is ISS being served by the TDRS? I do not understand the typical NASA terminology around this area. Can you help me there?
I see. I could not tell you the detail. I cannot tell you the detail or what the capability of say, the ISS communications architecture is. I do not know I know that it has the capability to send and receive communications to the TDRS spacecraft. So I suppose it could be configured to act as a node to essentially relay communications from one to another. I do not know if that is necessarily done, nor how much effort it would take to put together that particular kind of configuration. So I know that the ISS is designed to make use of TDRS, but I couldn't tell you if it has been designed to be an integral part of the TDRS system.
Okay, thank you for that. I think you're right that it is not a resource of TDRS yet. It's probably like a client which makes use of the facility. You got something interesting going on your screen? Can you?
Well, what I'm showing there is a NASA press release about the TDRS, and the animation that we were just showing was a little display of the TDRS system, where you have the TDRS spacecraft themselves operating, I believe, in geostationary orbit and acting as communications spacecraft, as communications nodes, aiding communication between say scientific spacecraft and manned spaceflight assets as well. So it provides high reliable, high quality, high bandwidth communications, and real-time communications too between the different assets.
Excellent.
And TDRS is an ongoing mission. It's been around for a long time.
Yeah, recently it seems like they're sending 2 more nodes, as I call it, the TDRS-L and TDRS-K, I believe.
Right.
Continuously expanding their infrastructure up there.
I don't know if expanding is necessarily the right term, because some of the TDRS spacecraft are extremely old, and they're definitely going to be showing their age. So they're going to reach their end of life, and if we don't maintain or replace those assets, you're going to have great gaps in the communications infrastructure. So it's an ongoing infrastructure maintenance and development cost for that capability.
It's 11:30.
All right.
Yeah, the other aspect of that is that some of the assets are pretty old and do not take advantage of newer technologies, and so it's important to put the new assets up there so that you can take advantage of the new technologies that have been developed over the years.
Interesting. I can imagine the interoperability and compatibility of 30, 40 years of experience in sending different missions and able to talk the same languages should be quite interesting and challenging.
Well, they've been pretty good about maintaining the communications capabilities and keeping they design complete solutions, and many of those communication solutions and standards have been around for an extremely long time. There's some design inertia in that, because people need these communication solutions to last for decades, simply because that's the lifetime of many of these. That's the lifetime of the needs of many of these systems.
Okay. All right. I'm good, and thank you for doing all this interesting views and sharing, and we'll continue to catch up with TDRS at a later date when it becomes again relevant and significant and important.
Right? Definitely.
So we do have a few things that we need to talk about, but do we want to keep that in the broadcast or stop broadcast and talk personal?
Well, first of all, is there any news that would be relevant to folks who are interested in putting cube technologies into space or around the moon?
Would you kindly repeat?
What do we have to talk about that is of broad interest? For example, is there any news from the CUBE spacecraft world?
No, this our intention is to kind of see what's out there. For example, if we are able to get hold of somebody from ESA, obviously they have their own communications systems too. Japan has theirs, but these are the few dominant players.
Mm-hmm.
When we are saying that we'll have a deep space information system, we want to kind of compare that all side by side and kind of show how the schema that we have or propose versus the utility value that we may bring, how that kind of matches. Okay, cool. I can see a big screen with lots of entries. Can you kind of
let's zoom into that.
Yeah, okay.
You mentioned communications and the different standards that we're after. I came across an excellent report written by Brian Clough, I believe he pronounced his name Clofas. There's an SRI report where he talks about communication systems of CubeSats in CUBE spacecraft, and he also has a few notes about lunar-oriented deployments as well, lunar-based communication out to CubeSats or CUBE spacecraft. And this is on his website, clofas.com, and it has a very nice listing of the different radios and communications techniques being used by many different spacecraft, and keeping track of what's going on with the CUBE spacecraft community. Just take it like green are university CUBE spacecraft, red are commercial or private, and blue are United States government. So he's keeping track of these as time goes on. It's a really nifty resource, and you can see what people are looking at in terms of the bands that they're using and the sorts of power performances they're looking at as well. So it's a really nice service that he's put together with this particular communications table. So this is a resource that we'll probably come back to.
Oh, thank you. I think that's very useful. All right. Anything else?
Nope. That's it for me for now.
Okay. So just as a small note, what I'm hoping that it may turn out, due to the inexpensive nature of the CubeSats and its approach, a TDRS-like relay infrastructure can be substantially made with today's technology using a mobile constellation. Right now, the TDRS relies on a geostationary object where it is always guaranteed, and they're always looking at a fixed point in space. This guarantees that at any point in time, the TDRS does not lose connectivity between the assets, the ground station, or like ISS or whoever it may turn out to be. In our case, like, we may choose to operate, we do not know, we have to get all the specialists' views. If you look at some of the attempts earlier done by Iridium, they were successful and they're still commercially working and making money. And things like Teledesic is another constellation which was designed on paper many years ago, including Microsoft and financial giants at that time. but it didn't happen. So they were talking about a node of some phenomenal number of 800 nodes, which it kind of covers in 10 different planes and all quite complicated and sophisticated. But the net out of it is we have enough number of nodes floating around. Yes, there will be disruptions and disconnections, and somebody will appear on the horizon, disappear on the horizon. All that will keep on happening. But overall, the quality of the service for the cost that we pay will be a trade-off. If you know what exactly mean, a cost comparison in the telephone quality, we used to get the toll quality in the mid-80s that we have been experienced with. Now we are able to get sometimes better quality than that in the voice over IP implementation. Sometimes it's terrible, but the technology has moved up using very efficient bandwidth conserved. You're able to get a lot more bits for your dollar. I see that comparison may take us into our CubeSat or LunarCubes like nodes that contribute to the first level of TDRS-like system. Okay, so that's only my guess. What do you think? Like,
Well,
yeah, go ahead.
The engineering and the physics of that sort of system is pretty well understood. So it's pretty easy to pull together a model that would be able to let you experiment with different network architectures and figure out what would be required to get a certain amount of system performance. There are some interesting questions about, for example, lunar orbital dynamics, because that's an important trade-off there. Because to get your signal quality up, you want to get the power up, or if you can't get the power up, then you get things closer together. But if you get too close to the moon, those low lunar orbits are not terribly stable, and you want your assets to be able to have a significant lifetime, or at least to last long enough to reach their mission goals. So there are some interesting questions to answer there, and it'd be a nice set of models to run and set up a trade space where you could start to figure out what you'd need to do, and because you have so many assets going to the moon, perhaps a nice general model or simulation that would allow you to see what you could do on an ad hoc basis would be something that would be interesting to see what sort of lunar communications network you could put together.
Excellent. Good thoughts. Yeah, I agree with you. All right. It's 11:40 Pacific time right now.
Yep. Yep. There was the lunar. You had your lunar meeting in Florida just a few weeks ago. Is there any continuing news from that?
Oh, sure.
Might be able to share with whoever might find this at some point in the future?
Yes, thank you for bringing that up. I'm sorry if I kind of forgot about that, because it's almost close to a month now. What we had was a lunar science applications workshop sponsored by Flexible Engineering, and pretty much the entire program was designed with Pamela Clark's brilliant leadership and Russell Cox supporting the focus on what we do for making it interesting with Kennedy Space Center. We had a phenomenal participation at Kennedy Space Center, and we had quite a few big guys show up in person and address several keynote speeches. What was technically interesting is they have the cryogenic division, like the very, very low temperature science group is also kind of located down there. They showed up with very many interesting things. And there is also, what was that, if I can say, there is a test facility I think they're building that may enable CubeSats to be tested effectively and inexpensively. So that was one thing we found. And there were a collection of about 10 or 11 different labs which complement several deep space technologies. And they're also starting to become available for commercial use as well. What else did we find it interesting? There was a group that presented a 3U CubeSat, which is essentially a environmental monitoring along that travel. Like, so wherever you're getting into the orbit, all the orbital dynamics and all the measurements that happen during the launch phase and deployment phase and a few other things, there was one project that is coming out of that. There were also interesting discussions about several ground stations and a initiative that might come up how to use Kennedy Space Center technical expertise to additionally volunteer or help this CubeSat community. And there are a few other things happening, and this is generally the 5-minute nutshell that comes across to my mind. And did you hear about anything specific that I can go into, Michael?
Well, at this point, no.
Okay.
Well, at this point, no. I found that bit by Clofas, which I found to be very helpful. And also, just you mentioned 3U, just in case anybody is watching. Here is an article from space.com in which Russell Cox played a significant part in providing some of the content. Here's a student holding a CubeSat of this image from Robert Sanders. He's holding a 3U CubeSat, actually. So when you say a 3U CubeSat, this is about the size of that spacecraft.
Awesome. Yeah, that's good. That's good.
Okay. So I think that's about all I have for today.
Okay. So we have a few more things to catch up on the side. So if you think it's 11:45 Pacific time, if you think we can stop the broadcast, then we can switch back into our discussion for 15 minutes.
Sure. Let's do that, and thank anyone for watching, for participating or seeing us today.
All right. Come back next week. We'll have a communication segment presentation.
Very good. Thanks.
Thanks.